All right, perfect. Good evening, everyone, and good evening, Mannheim. This is also my first time in Mannheim. I'm based out of Stuttgart. Not the best place to be in, to be honest. But well. So all right, so I'm going to be talking about boring stuff today. So I'm going to set expectations right here. So I'm going to be talking about ASR. ASR is automatic speech recognition. So if you've ever come across, Google Assistant, Siri, all sorts of stuff like that, then you have come across ASR. ASR, in its most simplest term, is essentially taking this speech, right? Whatever I'm saying right now is taking that and converting it into it's time for lunch, or essentially converting it into text, right? That's the main goal of ASR. What I seek to do by the end of this this talk is to convince one of you at least over here to try and experiment around some of the models that I'll be talking about today, right? And also try and see if you can incorporate leveraging this sort of unstructured data in your day-to-day job. So if one of you do that, that'll be great. Tweet out to me. I'm at reach_VB. All right, let's get to the fun stuff, right? So what is automatic speech recognition, right? So I have some sort of a waveform. I take that and I convert it into text. Right? Sounds easy, right? Sounds simple. It's just taking some audio file and then just essentially getting some text out of it. We have a billion models out there. There are insane number of research labs working on this. Then what's the complicated bit here, right? Let's try and see this a bit more in detail, right? Like, why is it not so simple? What you see on the screen right now is a spectrogram, or rather is the waveform representation of 3 words. The first one is ved, the second one is yell, and the third one is ben. 3 words, right? Simple words that we say every now and then. Now, if I was talking about ASR, if I was just talking about a machine learning model, right? If I was just talking about an algorithm which takes some sort of speech in, processes it, and gives me some text out, then that particular model would fail in this scenario. Can anyone tell me why?
I think because we have phonetics and we have geographical representation does not always match.
Exactly, yes. So the way we deal with sound is very different than the way we deal with, say, text or numbers. Numbers are unique. So 1 would always be 1 in any language, in any geography, in any any sort of situation. Same as text. So my name VB would be VB in any context whatsoever. However, if I, VB, who is an Indian, if I say something in German, my pronunciation would be very different than Alex saying the same thing in German, right? Of course, he would be more charming in that, but sure, right? So the way we pronounce things is different. The way anyone says things is different and varies a lot, right? Let's take, for example, good morning. I can say good morning, or I can say good morning, right? Or I can say good morning, right? I can say it in n number of different ways. Now, if this was an algorithm, how would you try and reconcile all of these different variations to good morning? So that's what we're going to try and sort of see, or like that's what we're going to try and unravel in the next couple of minutes. Or well, at least we'll see where we get to. What we see on the screen right now is different variations of right? So in the word ved, you see it's like ved. So like the variation of is sort of more like it goes above, like you have more sort of emphasis as you say ved. Same in case of yell, it starts off at a high note and then goes down. In case of ben, it's sort of same. believe it or not, this is still the same sort of phonetic element. So it's still eh, right? So all three of these correspond to the same character, correspond to the same text. So that's what makes it tough, right? Let's look at another variation. So now what you look at is 4 words. This is ve, re, me, ne, right? All of these simple words, with different context, we have different sort of waveforms, right? So I hope by now you understand that context in this case matters a lot, right? And what you also understand is that it's not as simple as just like writing an if-else statement saying that if you see a pattern like this, say that it is this character, right? It's a bit more nuanced than that. Now let's see how sort of modern architectures look at this. Let's see how our previous generations solved this problem as well. So a quick blast from the past. How we previously used to do it was we had some sort of a speech, right? And we would get some sort of features out of it. These features in most cases were MFCC features. If you don't know what MFCC is, think of MFCC features as a black box. You get different sort of different composition of the speech itself over time, right? So you have different things like how loud was the sound, what was the pitch of the sound, and so on and so forth, right? Assume those as features, then we would pass it through a perceptron, which is nothing but a like a very simple neural network, and you would get probabilities, right? These probabilities would be, hey, this particular waveform corresponds to the letter A, corresponds to the letter B, corresponds to the letter C with 90% probability, with 10% probability, and with 0% probability, and so on, right? That's it. That's how we used to do it before, and then we used to use some sort of fancy HMMs, and we used to get a sequence out. However, this did not scale well. This was one, time consuming. This was two, this required too much of effort and compute for us to sort of build and like run and so on, and more often than not it was just slow, right? And also it was like, imagine this, like for every transcription you're just like running this algorithm again and again and again and again and again, and then like getting a sequence out. And plain and simple, this is boring, right? Let's try and make this more fun. So this did not scale well, and that is why we did not have Siri back in 1980s. Sorry about that. But yeah, let's see what do we do now, right? So now we still have the same waveform. We have the same waveform, so we still have the same sort of sound wave which says it's time for barbecue. Hints at Alex for barbecue. And then we have some sort of future computation. So we again get like different sort of composition of the waveform. So we get Mel spectrogram per frame. We get how loud it is. We get how what's the pitch, and couple different things around this, and we pass it to an encoder. Now, what is an encoder? An encoder is again a neural network which tries to understand what has been passed to it, right? So in the most simplest terms, it basically understands the context of what's passed to it, right? So if it was a waveform, it would try to connect different words with individual words within the waveform, and it essentially helps us to solve this problem, wherein for different characters I have different variations, so it tries to learn these variations, so that every time there is an eh in between W and D, it would it would say that, hey, this is EH, right? So that's what the encoder learns essentially, and then we get to the decoder stage, and decoder basically says, hey, this particular 10 millisecond waveform corresponds to I, the other one corresponds to T, and so on and so forth. And through this encoder-decoder architecture, we get the output, which is it's time for barbecue, and so on. So that's basically it. That's how like modern architectures of ASR work. However, as I mentioned, if this would have been solved by now, I wouldn't be here talking about it, right? So there are definitely multiple problems with this. Now let's look at two of these key problems and how do we solve this in academia right now and in production as well. So the first problem is a single word might be just 5 letters long, but it may take 2 seconds. So take for example food. Food. When I just say the word food, I can say the word food just in less than a second, or I can just be like food, right? Or I can be like, dude, where's the food? Right? I can say it as fast as possible. I can say it as slow as possible. I can say it in different variations, and different dialects of the language would support would have different ways of saying it as well, right? So what this means is that the same 5 letters might take different time over here, So when I'm decoding, like my input still remains the same, but my decoding at the time of decoding, I might have different variations of this transcription. So how do I deal with that, right? Or rather, how do I deal with different dialects? How do I deal with different demographics? Or how do I deal with different lengths of waveforms which all correspond to the same text, right? The way we do that right now is by just concatenating different features. So I split the waveform into 10 millisecond snippets, and I concatenate sort of the previous vector, the next vector together, and I pass 3 sort of 3 feature sets together. So we go back to the same example over here. So in this case, I will pass the 10 milliseconds of W, the 10 milliseconds of E, and the 10 milliseconds of T all together to the waveform, so that it gets more context and it is able to sort of process faster, so it's not slow, right? And then hopefully it gets more context as well, and we get to its time and so on, right? So this is still simple. Like all I have to do in my code is just like essentially change 2 things, and I will still be able to get a transcription. But how do we meaning the model itself, know which part of X, which is the audio, maps to which part of Y? So how do we know in this example, in this waveform, which part of this waveform corresponds to I, which part of this waveform corresponds to T, which part of this waveform corresponds to S, and so on. Like that's like, think of it this way, like the model does not have any other information than just the waveform itself, right? So how does the model sort of figure out which section, which subsection of the waveform corresponds to what, right? And that is literally $1 billion question. There's an entire meta AI team which just focuses on that. There is like Google AI research speech team which just focuses on that, and so on. And I'm going to give you like one such example, and I'm going to give you some code bases that you can look at, as well as some demos through which you can like play around with it in just 2 minutes about it. But remember, the problem here is that we want to figure out which part of the audio waveform corresponds to which text, right? The $1 billion question. The way we do that from both like an academic standpoint as well as from a research standpoint is by using something called connectionist temporal classification. Don't worry, I'm gonna break this down. So what CTC does is that instead of me saying this part of the waveform belongs to the word it or belongs to the word BBQ, what it does is it splits the entire waveform into 10 milliseconds and tries to get one output for each of those, right? So if I have a 1 second long clip, it would break it down into 10 milliseconds, and for each 10 millisecond snippet, it would try to get 1 character output out, right? And then it tries to sort of find a fun way to collapse it all and get a letter. If that did not make sense up until now, it will make sense in the next slide. So what you see over here is an example of how CTC works, right? So we have the input, which is a 14 millisecond, a 140 millisecond input, so a 140 millisecond waveform. We split that into 14 snippets, so like 10 millisecond each snippet, x1, x2, x3, x4. This goes into the whole encoder-decoder thing that we spoke about, right? And And then for each of these input, it tries to give me one output. So the first x1 belongs to D, the second x2 belongs to I, the third one, maybe did not have any sound, so it just gave it like a null character. The fourth one belongs to N, and so on and so forth, right? So this in this context was something like dinner, right? So that's how this was said, and its transcription would be like in the first phase would be that I get individual character outputs, and then what CTC does is it merge duplicates, right? So you see that there was DI, then there was like no voice, then there was two N's, those two N's got collapsed, right? And now I have N, and then there was a break, there was another N, then there was E, and then there were 4 R's. They all got collapsed to R, and then break, right? So what's happened here is essentially we mapped a large feature space, so a 140 millisecond feature space, down to a word, dinner, right? And this is how we sort of solve the problem of varying time frames. So now you can say something like dinner, and it would still give you dinner, right? Hopefully you won't say it like that, but if you do, then there is way to solve for it, right? And what this also sort of helps with is that irrespective of how you say, it would be able to run, learn all of these, multiple alignments and still be able to produce the same transcription. So all the different transcriptions you say over here, like see over here, have the same, have the same output, which is dinner, because all of these collapse into the same thing. And to be honest, when I started researching, this was the bit which basically made me fall in love with the whole research side of speech. And it's honestly just 4 lines of code. That's it. I have it like later on for a brief demo. You can look at it, or you can chat about it with me afterwards as well. But basically, this 4 or 5 line of code is what solved or like got Siri on your iPhones, is what got Google Assistant on your Android phones, and so on and so forth. And that's how like ASR essentially works, right? So just to like sort of summarize, break your waveform into small pieces. For each waveform, get some sort of a character output, and then collapse them, right? That's it. Now that we've sort of done we've gone through like some sort of like theoretical part of it, what is the current state of the art? What is the Facebook of the world? What is the Google of the world using right now on their phones, like on their applications? So there is Wave2Vec 2.0. There is Data2Vec. I have linked the papers, but essentially what they do is, and this is a bit beyond the scope of this talk, is they use transformer type architectures masked audio modeling to learn ASR. There is conformer, which is a convolutional augmented transformer, and then there is ContextNet, which is a sort of slightly old network before the sort of transformer era, and all of these still work, right? And in case you want to try these out, in action, then you can try these out on Hugging Face. Right now, so I can actually give you a demo of this. I have linked this in my slides as well. So what we have right now is a small audio file which says something like, I don't know if we have audio here though. Oh, crap. Anyway, like I can share the link to this in a bit, but basically what this demo does is you can basically record any sort of audio. Over here, you can actually let's try and record something. Okay. Hello, my name is Weeby. I don't know if that worked. Let's see. It's sort of like trying to. Oh, it gave an error. Of course. Why would the demo work in the first place? But anyway, because I knew that this would not work, so I have a cached demo already, which says something like, "Hey, it's time for boiled potatoes," or something like that. The usual stuff that you say to your friends. But essentially, what this does is it uses the CTC algorithm that I said with different variations and tries to get like, you know, its intended transcription out. Nice. And what's happening here is it is using the same sort of state-of-the-art architecture which I spoke about earlier, which is Wave2Vec 2.0, which is currently the best out there. And you can of course try that out. You can also try these models out directly on Hugging Face. So you can go on the links below. These are open source, so you can use them for any of your dev-related activities and so on. So just feel free to sort of plug and play these. You don't have to sort of pay for any of these. All of these are available for free. And that's about it. Thank you so much for tuning in for my talk. I hope I did not bore you that much. And if you have any questions related to speech, related to audio, feel free to find me after this, or you can tweet out to me at reach_VB, or you can email me. I respond to pretty much every email that I get, and I love chatting about boring stuff. So thank you so much.